So when last we left, we were looking at VSEPR theory, valence shell electron pair repulsion theory. And it talks all about, the whole basis of that is that the areas of electrons around a central atom are pushing each other apart as much as they can. So they find optimal arrangements. And after the advent of VSEPR theory, experimental evidence showed that a lot of it was really, really correct. So scientists needed to find a way to explain better why the shapes that we've determined were correct were happening. And so what they came up with was valence bond theory. And the idea about valence bond theory is that it's all concerned with direct overlap of orbitals forms bonds. Okay, covalent bonds. Right? That's the main idea with valence bond theory. And so if we take the ideas from VSEPR, and I'm going to use a lot of images in this particular section of this lecture because my drawings they would be painful for you to try and decipher. So if I take this idea about overlapping orbitals and I apply it to VSEPR model of methane, CH4. What it does is it is all of the p orbitals, so taking a look down here, these are the p orbitals of carbon, and they exist in the x, y, and z directions, right? And so if VSEPR is correct, completely correct, then these three orbitals, these three p orbitals, will orient themselves as far apart as possible, just like it's shown in this particular drawing. So if I overlap my hydrogen 1s, so these are all hydrogen 1s orbitals, right? Because that's all hydrogen has to play with, right? And if the hydrogen 1s overlaps with p orbitals directly, like we see here, what I end up with is something that will have 90-degree bond angles. Okay, and that's not what they determined experimentally. We know that CH4 makes a tetrahedral thing, and we get 109.5 degree bond angles. So there's some conflict here. Okay, so they were trying to explain this, and so they figured, well, let's try to combine atomic orbitals. Okay, so if I have a 2s orbital from my carbon, so this is my orbitals from carbon, and if I arrange them in order of energy, so looking at the energy here on the left, the energy arrow is going up, so higher up is higher energy. My 2s is lower in energy, and my 2p is higher in energy. And my carbon has got 4 valence electrons, so 1, 2, 3, and 4. Okay, if I combine those 2s and those 2p orbitals, what I can do is get 4 orbitals, each with an electron. Okay, and they'll be slightly lower in energy. Slightly lower in energy than the p. Okay, so what we get is if I have 3 p's and 1 s orbital, if I combine those, what I get is s, p, 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 or what we refer to as sp3 hybridization. Hybrid. Okay, so if I take 4 atomic orbitals, so over here I have 4 atomic orbitals, okay, I should get 4 hybrid orbitals. Right? So I'll have 1, 2, 3, 4 sp3s. Okay, and then again, that comes from combining 1 s orbital and 3 p orbitals. Okay, so I get these hybrid orbitals, and what they do is and this is showing the same thing, is what they do is they combine, right? So if I take my 1s orbital and I combine it with 3 p orbitals, what it does is it alters the shape and orientation of all 4 of those orbitals. So now I have 4 hybrid orbitals, 4 hybridized orbitals that have slightly different shape and orientation. And when I put those all together, ta-da, we are left with tetrahedral geometry. Okay, so let's take a look at how we can look at the molecular shapes of different things. Okay, so determining the hybridization, okay, that's what we want to do. We want to determine hybridization around a central atom or any particular atom. Okay, so just like we did in the previous section, we were determining geometries about a central atom. I'm going to use similar tactics to determine hybridization. Okay, so with things that have a linear shape, what you want to do is count the areas on the central atom, just like you did when you were determining geometry. So with my carbon dioxide here that I'm showing is a linear molecule. It has 2 electron areas, no lone pairs. So I've got these 2 areas, right? 2 areas around the central atom, you're going to combine an S and a P. So you're left with an SP hybrid. Okay, so if I were to label this, I would label that central atom as SP hybrid. Okay, because I've only got 2 areas, an S and a P. All right, so to sort of look at how that is arranged, as far as my energy diagram, right? Talking about carbon there, he's got his 4 valence electrons. And I'm going to take and combine 1s and 1p orbital. Okay, so we'll end up with 1, 2, 3, 4. Okay, and what we have up here on the top right, these are unhybridized p orbitals. Okay, so there's 2 p orbitals that have electrons that are not going to participate in anything. Okay, at least not directly. And a little bit later on, we'll look at some diagrams which will help to illustrate this better. Okay, so I've got 2 hybrid orbitals, 2 sp hybrids, doing all my bonding in carbon dioxide. So let's look at our next type of shape, which was trigonal planar shapes. Right? So again, we're going to take a look at how many areas of electrons there are around my central atom. There are 3. So I've got 1, 2, 3. So 3 areas. So I've got an S, a P, and a P. Okay, there's 3 things there to go with 3 areas. So we'll call this an sp2 hybrid. Right? And if I were to label, I would call that carbon sp2 hybridized. Right? So looking again at our arrangement of electrons from that carbon, when I hybridize them, the hybrid orbitals have slightly less energy than the p orbitals originally did. Right? And again, up here in the upper right, this is an unhybridized, hybridized p orbital. Okay, so sp has 2 unhybridized p orbitals. sp2 has 1 unhybridized p orbital. So let's take a look at tetrahedral shapes. 4 areas. 1, 2, 3, 4. 4 areas. S plus P plus P plus P. sp3 hybridized. Okay, so an S and 3 P's, that gives me sp3. So I would label that nitrogen as sp3 hybridized. Okay, so our nitrogen's got 1, 2, 3, 4, 5. And I'm going to put all 5 of those in 4 new sp3 hybrid orbitals. 1, 2, 3, 4, 5. Okay. Notice that I've used up all my p orbitals, so I don't have any unhybridized p's. No unhybridized p's. Okay, so the takeaway message here is count the areas of electrons, and that many areas will tell you what the hybridization about a particular atom is. Okay, so taking a look at how that sort of plays out. So methane is our CH4. And if I were to draw a Lewis structure for CH4, it would come out like this. And if we wanted to know what the hybridization was, we would say there's 1, 2, 3, 4 areas. We would say S, P, P, P. 4 things means sp3 hybrid for that carbon. Okay, so the other important thing is that each one of these bonds is an sp3 bond. Okay, each one of those is an sp3 orbital. That means that I have 4 sp3 hybrid orbitals. Okay, and they each directly overlap with the 1s of the hydrogen. The hybridization itself is why they orient in the 109.5 degree bond angles. Okay, ammonia. Remember, ammonia has a tetrahedral electron geometry, right? But a trigonal pyramidal molecular geometry, right? So our bond angles are still about 109.5 degrees because that's determined by our electron geometry, right? And we've got NH4 plus, so our Lewis structure for that would, excuse me, it's NH3, my mistake. Ammonia, NH3. Right? So again, determine how many areas of electrons you have. Let's change the color a little bit. So I've got 1, 2, 3, 4 areas equals sp3. Okay? So your molecular geometry does not determine hybridization. Okay? Let's make a note of that. Okay? The electron geometry determines hybridization. So you count the areas just like you would determining electron geometry.